All right, let's jump right into this deep dive. We've got a stack of source material here, all focused on mathematical tools for exploratory data analysis and feature engineering. Our mission today really is to get beyond the absolute basics you might already know, like mean and standard deviation. We want to unpack how certain tools for measuring variability, understanding distribution, and importantly, quantifying relationships between variables can give you a much, much richer picture of your data. And ultimately, how that helps you prepare it effectively for, whatever analysis or modeling you're planning.
That's right. We'll be looking at some specific, pretty powerful concepts, things like mean absolute deviation, or MAD. We'll dig into quantiles and percentiles, understand the coefficient of variation, or CV, and then, crucially, explore covariance and correlation, including how they appear in matrix form when you're dealing with lots of variables. These are, well, they're truly foundational for pulling those nuanced insights out of your data set.
Okay, foundational. So let's unpack that. Most people looking at data, they're familiar with the mean, the average, right? And maybe standard deviation to get a sense of spread. But the material you've shared, it introduces some really interesting alternatives, deeper ways to look at this stuff. Let's start with mean absolute deviation, MAD. What is that exactly, and why might someone choose to use it over standard deviation?
Okay, so mean absolute deviation, or MEMD, it measures the average distance of each data point from usually the mean or the median. But here's the key difference from standard deviation. It uses the absolute values of those distances. It doesn't square them.
Ah, okay, so it stays in the original units of the data then. If our data is in dollars, the MAD is also in dollars.
Exactly. That's a big plus for interpretability. And because it doesn't square those deviations, especially the large ones from outliers, it's inherently less sensitive to extreme values compared to standard deviation. Standard deviation, really penalizes those outliers because of the squaring effect.
Right, right. So it gives, like the material says, a more robust, interpretable view of spread. I quite like the analogy in there, calculating the average walking distance from the center of a park. MAD feels like it gives you that realistic, sort of human-scaled average distance, one that isn't totally thrown off if one person decides to walk, miles away from the center.
That's a really good way to put it, yeah. You probably lean towards MAD when you suspect your data might have significant outliers, or when you really need that intuitive interpretation of spread directly in the original units. It's useful in, say, outlier robust analytics, or maybe assessing consistency, where you don't want extreme fluctuations to disproportionately skew your measure of typical variation.
Interesting. Okay. So moving on from spread to understanding the overall shape and like specific points within the distribution, the sources talk quite a bit about quantiles and percentiles. How do these help paint that picture?
Well, quantiles and percentiles, they're all about dividing your data, once it's ordered, into equal-sized chunks based on rank. Percentiles are just a specific type, the most common maybe, where you divide the data into 100 equal parts. Quantiles is the umbrella term. It includes percentiles, but also things like quartiles splitting into 4 parts or deciles into 10 parts and so on.
So when we talk about Q1, Q2, Q3, that's quartiles. The 25th percentile is Q1, the 50th is the median, which is Q2, and the 75th is Q3.
Precisely. And a value at, say, P90, the 90th percentile, means that 90% of all your data points fall at or below that specific value. The phrasing in the material is good. It's the value below which a certain percentage of the data falls.
That below which point is really key, isn't it? The analogy they used about height percentiles in a classroom was helpful. If you're in the 90th percentile for height, it means 90% of your classmates are shorter than you are. It doesn't mean you're 90% as tall as the tallest person. It's all about your relative position in that ordered lineup.
Exactly. And they're super useful. They help you understand the spread and the skewness of your distribution. They give you a really clear way to identify potential outliers. Think about the interquartile range, the IQR method, which uses Q1 and Q3. Plus, they let you compare the relative standing of different points within the data. And they're even used sometimes for standardizing scores, like on exams or other metrics.
Okay, so we've got a robust measure of spread with MAD and ways to understand distribution points with quantiles. Now, what about comparing variability across data sets that might be on completely different scales? That seems to be where the coefficient of variation, the CV, comes in. What's special about that?
The coefficient of variation, CV, yeah, it's essentially a normalized measure of dispersion. What it does is express the standard deviation as a percentage of the mean. So think of it as the standard deviation relative to the average value of the data. It puts spread in context.
So mathematically, you're taking the standard deviation, dividing it by the mean, and maybe multiplying by 100 to express it as a percentage.
That's the basic formula, yeah.
Yeah.
Assuming the mean isn't 0 or, very close to 0, because then it wouldn't make sense.
Yeah.
The whole point is to remove the scale dependency.
Right. And this is where it gets really interesting, I thought. The material gives this fantastic example. Imagine you have two data sets. One has a mean of 100 and a standard deviation of about 7. The other has a mean of just 20, but the same standard deviation, also about 7. Now, standard deviation alone tells you the absolute variation is identical.
Right. But calculate the CV for both. For the first data set, mean 100, the CV comes out around 7%, pretty low. For the second one, mean 20, same standard deviation, the CV jumps to around 35%.
Wow, that's a huge difference. It really highlights how CV tells a different story. Standard deviation gives you the absolute spread, but CV tells you the relative spread. It answers that question. How big are these deviations compared to the typical size of the numbers we're dealing with?
Exactly. The runner analogy in the sources nails this. Imagine one runner competes in 100-meter races, and their times are consistently within, say, plus or minus 0.5 seconds of their average. Relative to 100 meters, that's pretty consistent low CV. Now imagine another runner competes in 20-meter sprints, and their times also vary by plus or minus 0.5 seconds. The absolute variation is the same, but relative to a 20-meter race. That's incredibly inconsistent, a really high CV.
So the CV gives you that fair comparison because it's dimensionless, it strips away the units. Makes sense.
Absolutely. And that's where you see it used in fields like finance, comparing the risk variation versus return for different investments. Or in quality control, assessing consistency across manufacturing processes where items might have different average sizes, or even comparing variability in experiments across different species or conditions.
Okay, so far we've been mainly focused on understanding single variables one at a time. But realistically, in ED and especially feature engineering, we're constantly needing to understand how variables relate to each other. And the material you shared really digs into covariance and correlation for this.
Yes, absolutely essential tools. These are fundamental for looking at multivariate relationships. Covariance, at its core, measures how two variables change together. It gives you the direction of a linear relationship. Is it positive? Meaning they tend to increase or decrease together. Is it negative? Meaning one tends to go up when the other goes down. Or is it near zero, suggesting no real linear association?
Like the analogy of the two dancers, if they move in sync, maybe both stepping forward, that's like positive covariance. If one steps forward while the other steps back, that's negative.
That captures the directional idea perfectly. The big limitation with covariance, though, is that it only tells you the direction, not the strength. And its actual numerical value is totally dependent on the scale and units of your variables. A covariance of 200, calculated from height in centimeters and weight in kilograms, is just a number. You can't directly compare its magnitude to a covariance of, say, 2, calculated from time in seconds and cost in dollars. They're not comparable apples to apples.
Okay, so interpreting the actual size of the covariance value is tricky, and comparing covariances between different pairs of variables, especially if they have different units or scales, is basically meaningless.
Exactly right. And that inherent limitation is precisely why we usually turn to correlation, specifically the Pearson correlation coefficient. It's essentially a normalized version of covariance.
Normalized how? By taking the covariance and dividing it by the product of the standard deviations of the two variables involved.
That's a calculation, yes. And that division process does something crucial. It cancels out the units and scales the resulting value into a fixed, easily interpretable range, always between nominal 1 and plus 1.
Ah, okay, that's the key. So Pearson correlation tells you both the direction and the strength of a specifically linear relationship. Plus 1 is perfect positive linear, minus 1 is perfect negative linear, and 0 means no linear relationship at all.
Correct. And now you can compare them directly. A correlation of plus 0.8 between, say, study hours and exam scores is definitively a stronger linear relationship than a correlation of plus 0.4 between rainfall and plant growth, regardless of the original units used to measure those things. It becomes dimensionless and universally comparable. Like that analogy of comparing speeds as a percentage of the speed limit, a 90% correlation is strong, just like being at 90% of the speed limit is relatively fast, whether that limit was in kilometer or MOLF.
Right, which then logically leads us to looking at these relationships when you have many variables all at once using the matrix forms, the covariance matrix and the correlation matrix. What exactly are those?
Okay, so a covariance matrix is basically a square grid, a table, that shows you the pairwise covariances between all the variables in your data set. If you have, say, 3 variables, it'll be a 3 by 3 matrix. The values along the main diagonal, running top left to bottom right, are actually the variances of each individual variable, because the covariance of a variable with itself is just its variance. And all the other cells, the off-diagonal ones, contain the covariances between each possible pair of variables.
So it's like getting the full picture, the whole network map of how every variable interacts with every other variable, instead of just looking at pairs one by one, like the weather sensors example. You don't just see how temperature relates to humidity. You see temp humidity, temp wind, humidity wind, all laid out together.
That's a great analogy. It provides this comprehensive summary of the joint variability across all your features. And it's really fundamental for many multivariate statistical techniques, things like principal component analysis, PCA, or optimizing financial portfolios where asset co-movements are critical.
But wait, if individual covariance values depend on the scale of the variables, does the covariance matrix inherit that same problem?
It absolutely does, yes. If your variables are on wildly different scales, imagine you have age in years, maybe ranging from 20 to 80, and income in dollars, ranging from 20,000 to 200,000. The income variable will naturally have much larger variances and covariances just because the numbers are bigger. This can make directly interpreting the relative magnitudes within the matrix difficult. More importantly, if you use this raw covariance matrix in scale-sensitive analyses like PCA, the variables with the largest ranges will dominate the results, potentially masking patterns in lower variance variables.
So you'd need to standardize your data first, like using z-scores to put everything on a common scale before calculating the covariance matrix if you plan to use it for something like PCA.
Exactly. Standardization is often a crucial pre-processing step when working with covariance matrices for those kinds of applications. Now, the correlation matrix, on the other hand, is structured similarly. It's also a square matrix showing pairwise relationships, but instead of covariances, it contains the pairwise Pearson correlation coefficients between all variables. You can think of it as the normalized version of the covariance matrix.
And since Pearson correlation is already dimensionless and neatly ranges from -1 to +1, the correlation matrix itself must be much easier to interpret directly, right? No scaling issues there.
Precisely. The diagonal of a correlation matrix will always be filled with ones, because any variable is perfectly correlated with itself. Every other value in the matrix, the off-diagonal elements, will be between -1 and +1. This instantly shows you both the strength and the direction of the linear relationship between any two variables, completely independent of their original units or scales. Much more straightforward to read and compare values across the board.
That makes it incredibly valuable for ED and feature engineering, doesn't it? I mean, identifying features that are highly correlated seems like a really big deal for modeling.
Oh, it is. Huge. The correlation matrix is one of your primary tools for spotting multicollinearity. That's the situation where predictor variables in your model are highly correlated with each other, meaning they carry redundant or overlapping information. Multicollinearity can cause serious problems in many models, leading to unstable coefficient estimates and making it hard to interpret the individual impact of each predictor. Seeing large absolute values close to 1 or -1 in the off-diagonal cells of your correlation matrix is a major red flag.
So you'd look at the matrix, maybe visualize it as a heat map, see those bright spots indicating high correlation, and think, okay, maybe I don't need both of these features in my model.
Exactly. It guides feature selection by highlighting redundancy. While you might use other metrics too, like the variance inflation factor, VIF, for a more rigorous check, the correlation matrix gives you that essential first-pass overview. It's key for understanding relationships, selecting features, and sometimes informs dimensionality reduction strategies too.
Okay, great. So Pearson correlation captures linear relationships. But what if the relationship isn't a straight line, but, the variables still kind of move together consistently? The material mentions Spearman correlation for that.
Right, good point. Pearson is strictly about linear association. If the relationship is monotonic, meaning as one variable increases, the other consistently increases, or consistently decreases, even if it's not along a perfect straight line, then Pearson might underestimate the strength of that association. That's where Spearman's rank correlation comes in. It's also useful if you're dealing with ordinal data that has a natural order that not necessarily equal intervals, or if you have outliers that might unduly influence Pearson's calculation. Spearman works by looking at the ranks of the data values, not the raw values themselves.
Ranks. So you sort each variable's values and assign positions, like 1 for the smallest, 2 for the next smallest, and so on.
Exactly. You rank each variable independently. If there are ties, you usually assign the average rank. Then you calculate the correlation based purely on these rank values.
And why is that useful? What does focusing on ranks achieve?
It makes the measure less sensitive to the actual magnitude of the differences between values and more sensitive to the consistency of the order or direction of the relationship. It's inherently robust to outliers because an extreme value just gets a rank at the top or bottom. It doesn't contribute an extremely large squared deviation like it would in Pearson. Think about comparing runner rankings across different races again. Spearman essentially tells you if runners tend to finish in similar relative positions, ranks, race after race, regardless of whether their actual finish times were seconds faster or slower in one race compared to another. It's about rank agreement. So, if we try to bring all these pieces together, MAD, Quantiles, CV, Covariance, Correlation, both Pearson and Spearman and their matrix forms, it's really a powerful toolkit. Each tool gives you a different lens, a different perspective, which is essential for doing thorough exploratory data analysis. They help you move way beyond simple averages to really understand variable spread robustly, grasp the distribution shape and pinpoint key values, compare variability fairly across different scales, and, crucially, for feature engineering, understand that complex dance of relationships happening between all your different features.
Absolutely. And for feature engineering, getting these insights is just gold. Using quantiles or MAD to spot potential outliers that need attention. Choosing the right measure like CV to compare consistency when maybe your features have different units. And perhaps most critically, using those correlation matrices to hunt down highly correlated features that could introduce multicollinearity and mess up your model downstream. These aren't just nice to haves. They feel like foundational steps for cleaning data, selecting good features, and ultimately setting yourself up for successful modeling.
And there's one more technique highlighted in the material that adds another useful layer: grouped descriptive statistics.
Ah, yes. Calculating these summary stats mean median, standard deviation, maybe even MAD or CV, but doing it within specific subgroups, like breaking down your data by a categorical variable, say region or customer type, and then calculating the stats for each group separately.
Precisely. It allows you to see if the patterns, the spread, or even the relationships between variables differ significantly across different segments of your population or data. That classroom grades analogy used in the sources works well here too. Looking at the average grade for the entire school gives you one number, but calculating the average and the variability per classroom might reveal significant differences, hidden structures, or disparities between classes. It's vital for any kind of segmented analysis, or even for checking for potential biases in your data.
Okay, wow. We've really covered a lot of ground. From MAD giving us that robust look at spread, quantiles helping understand distribution and outliers, CV for comparing relative consistency across different scales, and then that deep dive into covariance and correlation, their vital matrix forms, how they help us tackle critical issues like multicollinearity and even distinguishing between Pearson for linear and Spearman for monotonic relationships.
And the key takeaway, I think, is that these aren't just abstract mathematical ideas. Each one is a practical, hands-on tool. Each offers a unique perspective, a different angle, that's pretty much essential if you want to do a thorough exploration of your data and make really informed decisions when you're building out your features.
So thinking about this for you, the listener, as you approach your own data sets, what does all this mean? It means really thinking about the specific characteristics of your data and the questions you are trying to answer. Are outliers a potential headache? Do you need to compare variability across measurements that use fundamentally different units or scales? Is getting a handle on the complex web of interactions between many features absolutely crucial before you even start thinking about building a model?
Yeah, and that actually raises a really important practical question, doesn't it? With this whole toolbox available, MAD, standard deviation, CV, correlation matrices, covariance matrices, different correlation types, each offering a slightly different insight into variability and relationships. How do you actually decide? How do the specific properties of your data, its scale, its distribution, the presence of outliers, combined with your specific analytical goal, guide you in choosing which measure is the right one to use at each stage? When is MAD better than standard deviation? When should you look at a correlation matrix versus a covariance matrix? That's definitely something worth pondering as you embark on your next data exploration.